our favorite movies and books as children question what the future holds. So, will we be living on Mars in another century? Will we travel at the speed of light? Or will flying cars finally become the new norm? Although these ambitions seem far-fetched, did the Wright brothers really think that there would be fighter jets traveling at 3 times the speed of light? The point is, although we currently may not be capable of achieving our childhood ambitions, our never-ending imagination allows us to create technologies to get a glimpse of the future. One of my favorite technologies leads us down this path: magnetic levitation trains, or Mag-Lev for short. So, what exactly are Mag-Lev trains? Think of Back to the Future when Marty uses a hoverboard. Essentially, Mag-Lev trains bring this levitation dream to reality. Well, sort of. So, how do they work? To fundamentally understand how Mag-Lev trains work, think of the way magnets act. The north end of one magnet would repel the north end of another magnet and be attracted to the south end of another magnet. Similarly, a magnetic levitation train utilizes the same magnetic potential to move a train across a guideway. Currently, 2 systems of magnetic levitation exist: electromagnetic suspension, EMS, and electrodynamic suspension, EDS. In the first system, EMS, magnets are aimed in the corners and edges of a train's body, while magnets of the opposite polarity are placed at varying distances along the train's track, attracting them. But the question remains, how is the train supposed to move forward along the track if each of the magnets equally attracts the train? The answer lies in a feedback system. Essentially, the strength of the magnetic attraction of the magnets along the path are recorded, and when the train passes a certain threshold related to distance from these magnets, the magnet is then shut off, and the train is then attracted to the nearest following magnet. Variations of this system, including the trans-rapid system, employ magnets on the bottom of the guideway to further levitate the train off the ground, allowing for it to climb greater gradients. Other variations of this system employ the property of superconductivity, which is essentially the supercooling of magnets to further strengthen their magnetic attraction and allow for the trains to move faster and more dynamically. In the second system, EDS, rather than using the property of attraction and a feedback mechanism, it utilizes both the properties of attraction and repulsion to move the train along its track. In this system, coils are placed at varying distances along the train's track, each supplied with its own current. The current of these coils can also be flipped, which flips the polarity of the coil. So, when the train passes a coil, the polarity of the coil is flipped to that of the same polarity of the magnets on the train, repelling the train and pushing it forward, while magnets in front of the train remain the opposite polarity of the magnets on the train and attract it forward, allowing the train to move forward along the track. Unfortunately for the system, however, at slower speeds, the magnetic potential of the coils is unable to hold the train up, prompting the need for wheels. But variations of this system, including the SC Mag-Lev system, employ the same idea as the trans-rapid system I explained earlier, and place magnets on the bottom of the guideway to further levitate the train off the ground and counter the need for wheels. In both these systems, EMS and EDS, the loss of speed and consumption of energy associated with friction in wheeled trains is avoided, thus allowing for Mag-Lev trains to move faster and more dynamically. Mag-Lev trains also provide numerous other benefits over their traditional counterparts. Dominic Ziemke, the chairman of Integrated Transport Planning and Traffic Engineering at Technisch-Universität Dresden, in his study concluded that passenger transportation by electrified trains led to the emissions of 54 grams of CO2 per passenger kilometer, while passenger transportation by diesel-powered trains led to the emissions of 69 grams of CO2 per passenger kilometer. Not only do Mag-Lev trains provide a significant reduction in the emissions of CO2 and other greenhouse gases, but also provide lessened noise pollution and greater maneuverability. According to Cornell Wilson, a current NASA engineer, magnetic levitation trains are quieter than diesel-powered trains and can make tighter turns than high-speed rails. Not only do Mag-Lev trains provide significant advantages over the traditional train, but also over commercial airplanes. Stathis Elandis, a recipient of a PhD in physics from Stanford, in a study in fall 2010, discussed the benefits of magnetic levitation technology over various other transportation systems in Europe. In his study, he examined the relationship between speed and energy consumption of these various transportation systems. He regarded that Mag-Lev trains achieved a greater efficiency than most other transportation systems and proved to achieve the same travel time as a commercial airplane when traveling long distances. In another study published by Northeast Mag-Lev, the Boeing 777 was measured to emit more than 2 times the amount of emissions as their Mag-Lev counterparts. In these studies and more, the Mag-Lev train is seen as a significant transportation method, rivaling and sometimes even surpassing that of the commercial airplane. It is clear that Mag-Lev trains have the potential to revolutionize the way we travel and our future. Currently, however, magnetic levitation train systems are only present in countries where the government holds large shares in wealth and infrastructure, as the construction of these magnetic levitation guideways proves to be a significant financial burden. But with the right investment and dedication, we can make Mag-Lev trains a reality, one in which energy is clean and transit is cheap. So, as we move forward, let us come together as a society and work together towards making Mag-Lev trains our future. Thank you.